Welcome back to science, to sleep by the place where the universe slows down, and the stars whisper their stories to you. Tonight, we'll drift far beyond the edges of our solar system, into the cold and ancient corridors of space, where a mysterious visitor named 3I Atlas has rewritten everything we thought we knew about comets. So, lay back, let your mind float, and listen, because the cosmos is about to tell you a secret. In the infinite stillness of deep space, where the faint glow of distant stars flickers like the pulse of the universe itself, there are wanderers that travel between the stars, timeless, silent, and unbound by the gravity of any single sun. These are the interstellar objects, cosmic nomads, that drift through the galaxy, carrying with them the secrets of their birthplaces. The story of 3I Atlas begins long before it ever brushed past our sun. It begins in the dark, ancient outskirts of another star system, a place so distant that even light would take centuries to arrive. There, within a protoplanetary disk of gas, dust, and ice, a small cluster of matter formed. It was ordinary, perhaps, in its beginning, a frozen chunk of rock and volatile material, just like billions of others that circled their young star. But fate had something different in mind for this one. Over millions of years, gravitational chaos unfolded. Massive planets shifted in their orbits, colliding and rearranging the architecture of their system. One of those massive worlds, perhaps a gas giant the size of Jupiter, flung this tiny object out of its orbit with tremendous force. It was no longer bound to its star. It was free, adrift in the cosmic ocean. For millions upon millions of years, it traveled the interstellar void through magnetic storms, clouds of interstellar dust, and the soft light of distant suns. It was silent, untouched, and ancient. A frozen messenger bearing the fingerprint of a world that no longer existed in its original form. When it finally crossed paths with our solar system, humanity was ready. We had already encountered two other interstellar visitors, Oumuamua in 2017. And Borisov in 2019. Oumuamua was strange, an elongated, tumbling object that showed no cometary tail, but reflected sunlight in ways no asteroid should. Borisov, on the other hand, was unmistakably a comet, a ball of ice and dust that released gas as it neared the sun, behaving more like the comets we were used to, but still distinctly alien in its makeup. Those discoveries taught astronomers to keep their eyes open, to watch the skies carefully, because the galaxy might not be as isolated as we once thought. And so, when 3I Atlas appeared, it wasn't just another faint blip in the sky, it was a revelation. Detected by the Atlas Survey System, a pair of robotic telescopes in Hawaii designed to spot asteroids and comets that might pose a threat to Earth, it at first seemed like just another routine observation, but its trajectory, its speed, and the faint glow it carried told a different story. This was not an object born from our solar system. It was on a hyperbolic orbit, meaning it was moving too fast to be captured by the sun's gravity. Its velocity exceeded the escape velocity of the solar system itself, a telltale signature of something not native to our celestial neighborhood. Astronomers across the globe quickly realized the significance. This was the third confirmed interstellar object ever detected. Hence the designation 3I. The I stands for interstellar, marking its extraordinary journey through the galaxy. And the name Atlas honors the system that discovered it, a fitting title, for Atlas was the Titan in Greek mythology who held up the sky itself. The name symbolized strength and endurance, the very qualities this cosmic traveler embodied. But beyond the excitement of discovery, there was something profound about its existence. Each interstellar object we've encountered tells a different story, and together, they reveal the diversity of planetary systems scattered throughout the Milky Way. Oumuamua's strange, cigar-like shape and reflective surface challenged everything we thought we knew about how debris behaves in space. Borisov's traditional cometary activity, yet with a chemical composition distinct from anything seen before, suggested that other star systems could produce comets just like ours, but with ingredients we've never encountered. 3I Atlas, however, stood apart in another way. It seemed to carry the characteristics of both. blurring the lines between what we call an asteroid and what we define as a comet. its discovery forced astronomers to rethink how interstellar objects form, survive, and evolve during their lonely journeys through space. When an object is ejected from its home system, it experiences forces beyond what we can easily simulate. Gravitational encounters, radiation exposure, and collisions with microscopic particles drifting between the stars. These experiences gradually erode, reshape, and sometimes even reactivate its surface chemistry. By the time it reaches another star system, it might no longer resemble the object it once was. 3I Atlas offered scientists a window into that transformation, a cosmic time capsule that had traveled between worlds, carrying within its icy core the chemistry of its origin and the scars of its voyage. To understand just how rare such encounters are, imagine the scale of the galaxy. The Milky Way is over 100,000 light-years across, and within it, billions of stars orbit the galactic center, each with the potential to harbor planets, moons, and debris. Yet, the spaces between these stars are vast, so vast that an object could drift for eons without ever coming near another system. The fact that 3I Atlas found its way to us, during a time when our telescopes were advanced enough to detect it, is almost miraculous. It's a reminder that the universe is constantly in motion, even when we perceive it as still. For astronomers, detecting 3I Atlas was more than just another data point. It was a chance to study something that had experienced conditions impossible to reproduce in laboratories on Earth. By analyzing its brightness, motion, and subtle changes in its light spectrum, scientists could infer its size, shape, and composition. Every faint flicker of reflected sunlight told a story of minerals crystallized in alien environments, of ices that formed under different starlight, of radiation that had aged its surface for untold millennia. These observations also help us refine our understanding of how often such objects pass through our solar system. For decades, it was assumed that interstellar visitors were exceedingly rare, but the discovery of 3 in just a few years suggests otherwise. It implies that there may be countless such wanderers drifting unseen, too faint for our instruments to detect, but silently gliding past us. Some might even carry organic molecules, the very building blocks of life, hinting that interstellar comets could be one of the ways life's ingredients are scattered across the galaxy. In this context, 3I Atlas becomes more than an object of scientific curiosity. It becomes part of a larger narrative, one that connects the birth of planets, the migration of matter through space, and perhaps even the origin of life itself. It reminds us that our solar system is not an isolated island, but part of a greater galactic ecosystem, where materials are exchanged across unimaginable distances and timescales. For centuries, humans have looked at comets with a sense of awe and mystery. In ancient times, they were seen as omens, harbingers of change or disaster, but in truth, they are storytellers. Each comet, each fragment of ice and rock that streaks across the sky, carries within it a piece of the universe's memory. And when one comes from beyond our solar system, like 3I Atlas, it carries not just our story, but the story of another sun, another world, another time. As scientists observed 3I Atlas through telescopes around the globe, they realized they were not just looking at a comet. They were looking at evidence of another planetary system's history, a relic from an alien star that once shone brightly somewhere in the spiral arms of the Milky Way. Its journey to us spanned millions of years, crossing the invisible borders between stars, surviving cosmic rays, radiation storms, and gravitational distortions. And yet, it arrived intact enough for us to study, to learn from, and to wonder at. The cosmic visitor had returned not home, for it has no home anymore, but to a place where it could be seen, understood, and appreciated. In that way, 3I Atlas didn't just change what we know about comets. It changed how we think about our place in the universe. Every interstellar object that passes through our skies is a message, a quiet whisper from another world, telling us that we are not alone in the vast dark sea of stars. In the still hours of an early morning in 2024, the telescopes of the Atlas Survey, short for Asteroid Terrestrial Impact, Last Alert System, quietly scanned the night sky from their high perch atop Hawaii's volcanic peaks. Their purpose, as always, was to guard our planet, designed to detect asteroids that might one day cross paths with Earth. Atlas continuously monitored the heavens for faint, moving lights that betray the presence of objects wandering through our cosmic neighborhood. But that morning, the observatory captured something peculiar, a faint streak of light that didn't behave like anything in the known catalogs. Its trajectory was too steep, its velocity too high, and its brightness fluctuated in ways that made astronomers pause. What they were seeing was not an ordinary comet or asteroid bound to the gravity of our sun. It was something from beyond. As the data streamed in, the computers processed the information, automatically flagging the strange object for follow-up observation. Within hours, astronomers around the world were alerted to a potential discovery. When they began analyzing the trajectory, they noticed an unmistakable signature, a hyperbolic orbit. That meant it wasn't looping around the sun like a normal comet. It was flying past it once, never to return. Such an orbit could only belong to something that had originated outside the solar system. The realization spread quickly through the astronomical community. This was an interstellar object, the third ever detected, after the groundbreaking discoveries of 1 Oumuamua and 2 Borisov. The world of astronomy erupted in quiet excitement. For researchers who spend their careers studying distant stars and theoretical models of planetary formation, the chance to observe a real interstellar object is something extraordinary. Unlike telescopic images of exoplanet light years away, these visitors bring a tangible piece of another star system directly into our reach. And yet, there was something different about this one. The brightness of the object, later designated 3I Atlas, changed in unexpected ways. Its coma, the glowing cloud of gas that typically surrounds a comet as it approaches the sun, appeared irregular and inconsistent. It brightened rapidly, then dimmed, as if the surface were shedding material in sudden bursts rather than a steady stream. When scientists plotted its velocity, they found it was moving at an astonishing speed of over 30 kilometers per second relative to the sun, faster than nearly any natural object that calls our solar system home. At that speed, it was impossible for the sun's gravity to capture it. It had come from somewhere else in the galaxy, passing through our system for a brief and fleeting visit before vanishing into the void once more. The confirmation came within days. The Minor Planet Center, the official body responsible for designating small celestial objects, gave it the formal name 3I Atlas. The news made its way across scientific journals, online forums, and international observatories. For many astronomers, the moment brought back memories of the first time humanity discovered an interstellar object, Oumuamua, in 2017. That mysterious body had defied all expectations. It lacked the glowing tail typical of comets, was oddly elongated in shape, and exhibited non-gravitational acceleration, meaning it sped up slightly as it left the solar system, as if something unseen were pushing it. That behavior led to years of speculation, ranging from icy hydrogen sublimation to, more controversially, the idea that it might even be an artificial object, a fragment of alien technology propelled by light. Then came 2I Borisov, discovered in 2019 by an amateur astronomer in Crimea. Unlike Oumuamua, Borisov looked and behaved like a traditional comet, complete with a bright coma and a visible tail. Its composition, however, hinted at a chemistry unlike anything in our own solar system. By the time 3I Atlas appeared, scientists had already begun refining their models of interstellar visitors. But this new object defied even those expectations. Its orbital path was steep and precise, cutting through the plane of the solar system like a blade of light. Spectroscopic studies showed subtle differences in its reflected sunlight compared to ordinary comets. Some wavelengths suggested the presence of exotic carbon compounds, while others hinted at crystalline structures more typical of deep space exposure. Astronomers debated its nature. Was it more comet-like, made of ice and dust, or asteroid-like, composed primarily of rock and metal? The truth seemed to lie somewhere in between. What made the discovery so remarkable wasn't just its physical characteristics, it was the timing. The detection of 3 interstellar objects in just a few short years suggested something profound about the universe. For decades, it had been assumed that the space between stars was mostly empty, that objects flown out of their home systems would rarely cross paths with another. But the increasing frequency of these detections hinted that the galaxy might be teeming with interstellar debris, frozen fragments of planets and comets ejected during the violent births and deaths of stars. Perhaps trillions of them drift silently between suns, unseen until one happens to cross the narrow line of sight of our telescopes. In that realization lies one of the most humbling truths of astronomy. We are not an isolated solar system in a lonely corner of the cosmos. We are part of a vast, interconnected galactic ecosystem, where matter is constantly exchanged across unimaginable distances. 3I Atlas was evidence of that cosmic exchange, a visitor from another system, bringing with it the chemical fingerprints of a star we may never identify. As scientists examined its orbit more closely, they traced its incoming path backward through the stars. The calculation suggested that it entered the solar system from a direction near the constellation of Hercules, traveling through interstellar space for millions, perhaps billions of years. Its origin was impossible to pinpoint. Precisely the galaxy's gravitational tides and the movement of stars over time made it too uncertain, but it might have come from a young star system that once existed in that region. Some simulations even suggested that 3I Atlas could have been ejected from its home system shortly after its formation, meaning it had been traveling through space since before Earth itself had formed. The object's brightness continued to confound observers. Normally, as comets approach the sun, the increasing heat causes their icy surfaces to sublimate, turning from solid to gas and creating the familiar tail that points away from the sun. But 3I Atlas didn't follow that rule. Its brightness changed in unpredictable ways, sometimes increasing when it should have dimmed, and vice versa. This unusual behavior suggested that it might have a fragile structure, prone to fragmentation. Indeed, later observations confirmed that it began to break apart, scattering pieces of itself as it neared the sun. These fragments sparkled briefly, then faded, disappearing into the background of interplanetary dust. What made 3I Atlas so important to astronomers was not just that it existed, but that it gave scientists a new opportunity to test their theories about how planetary systems evolve. Every interstellar object we detect serves as a natural sample, a piece of another system delivered right to our doorstep. By studying its motion, composition, and behavior, we can infer what conditions might be like in other parts of the galaxy. If 3I Atlas contained unusual isotopes or molecular structures, it would suggest that its parent system formed under different environmental conditions, perhaps with more radiation, different chemical abundances, or unique thermal histories. The global collaboration that followed was astonishing. Observatories from Chile to Spain, from Hawaii to the Canary Islands, trained their telescopes on the faint, moving speck. Data poured in nightly, shared across networks that connected thousands of scientists. Even the Hubble Space Telescope joined the effort, attempting to capture high-resolution imagery of the object before it vanished from sight. Amateur astronomers contributed too, using backyard telescopes to track its fading light as it slipped farther away. In that shared effort, the world of astronomy became unified once again, connected by the wonder of an interstellar visitor whose presence was fleeting, but whose impact would last for decades. Each new measurement added another layer to the mystery. 3I Atlas's reflectivity hinted that it might have an unusually porous surface, perhaps filled with cavities where trapped gases escaped in bursts, causing its strange changes in brightness. Its composition showed traces of carbon-rich compounds that had rarely been seen in solar system comets, and its fragmentation behavior suggested a fragility that could only come from eons of exposure to cosmic radiation, which weakens materials over time. It was as if this object had been sandblasted by the galaxy itself, eroded, not by wind or water, but by the relentless bombardment of particles and radiation in interstellar space. For astronomers, 3I Atlas represented both a discovery and a mystery. It shook the foundations of cometary science because it didn't fit neatly into any existing category. It wasn't entirely like Oumuamua, and it wasn't entirely like Borisov. It was something in between, a bridge between the familiar and the unknown. It proved that the universe has more variety than we can easily imagine, that the processes shaping other solar systems can produce objects vastly different from our own. It was a moment of both clarity and confusion, where every answer opened a dozen new questions about what lies beyond our sun's reach. The discovery of 3I Atlas was a reminder that the universe is full of surprises. Even in an age when our telescopes can peer billions of light years into the past, there are still phenomena unfolding right here, in our cosmic neighborhood, that we are only beginning to understand. The faint light that flickered across the Atlas telescope sensor that morning was more than just a detection. It was a message from another world, traveling through time and space to tell us that the galaxy is far more dynamic, complex, and connected than we ever dared to believe. When 3I Atlas first appeared on the astronomical radar, scientists expected it to behave much like other comets that had entered our solar system. After all, comets, regardless of their origin, are generally predictable in their chemistry, a mixture of water ice, carbon dioxide, carbon monoxide, silicates, and a sprinkling of organic molecules. These icy bodies are remnants from the earliest days of star and planet formation, frozen archives of the primordial past. But as telescopes around the world began to capture the spectral fingerprints of 3I Atlas, it became clear that this object was anything but ordinary. Its light reflected not just the familiar signs of cometary ice, but a symphony of elements and compounds that hinted at a far stranger and more exotic origin than anyone had imagined. When scientists analyze celestial bodies, they rely on a technique called spectroscopy, splitting light into its component wavelengths to read the chemical signature of the object emitting or reflecting it. Each element and compound absorbs or emits light at specific wavelengths, acting like a barcode of its identity. As astronomers focused their instruments on 3I Atlas, the results they obtained defied easy explanation. The spectral data revealed unfamiliar absorption bands, regions where light was missing in ways not typically seen in comets of our own solar system. These bands suggested the presence of volatile compounds that had rarely, if ever, been detected before. It was as if 3I Atlas had carried with it the chemical essence of another solar system entirely, one that had evolved under conditions unlike anything we've observed. The first surprise was the object's apparent lack of standard water ice emissions. Normally, when a comet approaches the sun, the heat causes its water ice to sublimate, releasing gas and dust that form the coma, the bright halo surrounding its core. But 3I Atlas displayed only faint traces of water vapor, far less than expected for an object that had traveled so close to our star. Instead, its emissions were dominated by carbon-bearing compounds, not just carbon monoxide and carbon dioxide, which are common in comets, but more complex hydrocarbons that hinted at a rich organic chemistry. Some scientists suggested that 3I Atlas might have formed in a region of its home star system that was particularly rich in carbon, perhaps beyond the carbon snowline, where volatile carbon-based materials can condense and freeze. The implications of that were profound. In our own solar system, most comets form beyond the orbit of Neptune. In the cold reaches of the Kuiper Belt or the distant Oort cloud, these regions preserve ancient ices from the early days of the solar nebula, but the chemistry there is largely uniform. The diversity seen in 3I Atlas's spectral signature suggested that other planetary systems might follow very different chemical pathways. Its parent system could have had a unique ratio of carbon to oxygen or a different mix of trace elements. That alone would alter how ices, rocks, and gases condense during its formation, producing an object with an entirely unfamiliar molecular makeup. There was also an unusual pattern in the dust it released. Normally, the dust grains expelled from comets reflect sunlight in predictable ways, revealing information about their size, composition, and structure. But the dust from 3I Atlas scattered light in an erratic pattern, suggesting grains that were either extremely fine or oddly shaped. Laboratory simulations later indicated that such scattering could result from dust coated in exotic, Organic films, the kind that form through complex chemical reactions over billions of years of radiation exposure in deep space. These organic coatings could have altered the reflectivity and thermal behavior of the comet's surface, contributing to its strange brightness variations. As scientists compared the data from different observatories, a pattern began to emerge. 3I Atlas appeared to contain high levels of carbon-rich compounds, and possibly even refractory organics, complex, tar-like substances that resist evaporation. These are the building blocks of life, the molecules from which amino acids and nucleic acids can eventually form under the right conditions. To think that such molecules could have originated in a star system far from our own sparked both scientific and philosophical wonder. It supported the long-standing hypothesis that organic chemistry, the chemistry of life, is not unique to Earth, or even to our solar system, but a universal feature of the cosmos. The infrared observations deepened the mystery. Using instruments capable of detecting heat signatures at long wavelengths, astronomers discovered that 3I Atlas radiated energy in unexpected ways. The thermal emission didn't match the models used to predict cometary behavior. It was as if the object's surface was covered in materials that absorbed sunlight differently than the ices and silicates typical of comets. Some speculated that it might have a crust of processed organic compounds, the result of billions of years of exposure to interstellar radiation and cosmic rays. Such exposure would have transformed its outer layers, turning once clear ices into dark, carbonized materials similar to asphalt or soot. This would explain why its albedo, the measure of how much light it reflects, was so low. 3I Atlas absorbed most of the light that touched it, reflecting back only a faint, ghostly glow. But perhaps the most puzzling clue came from the object's fragmentation. As it approached the sun, 3I Atlas began to disintegrate, breaking into several pieces that quickly dissipated into space. The way it fractured suggested internal weaknesses. Pockets of gas trapped within the structure that burst open as the heat increased. Yet, even in its fragmentation, scientists detected signs of unusual chemistry. The ejected material contained dust grains with an anomalously high ratio of carbon to oxygen. That ratio was unlike anything found in comets of our solar system, pointing again to a distinctly alien origin. Some researchers proposed that the comet might have formed around a red dwarf star, type of star known for its high carbon abundance and intense radiation flares. Others speculated it could have come from a binary star system, where gravitational interactions and variable radiation create complex and chaotic chemical environments. This diversity in possible origins reminded astronomers of how varied planetary systems can be. In some systems, stars are richer in heavy elements, while in others, they are dominated by lighter ones. Each of these environments shapes the chemistry of the debris that forms around them. If 3I Atlas did indeed originate in a carbon-heavy system, then its composition could offer a rare glimpse into how such environments differ from our own. It was like holding a rock from another planet. Only this one came from another star entirely. In laboratory studies, scientists have long simulated what might happen to icy bodies that drift through interstellar space. As these objects are bombarded by cosmic rays, their surfaces undergo chemical transformations, creating new compounds that can survive the harshness of space for millions of years. 3I Atlas seemed to be a living example of that process. Its surface chemistry was not static, it was dynamic, constantly evolving as it traveled. The carbon-rich layer might have acted like a shield, preserving the interior ices from total sublimation, while also creating new molecules on the surface. If this process is common, then interstellar comets like 3I Atlas could serve as carriers of complex organic compounds between star systems, acting as seeds of chemistry that connect one world to another. Even as the object faded from view, astronomers continued to analyze the data it had left behind. The subtle variations in its spectrum, the timing of its brightness fluctuations, and the peculiar way it released dust, all of it told a story written in the language of atoms and light. Every observation added another layer of understanding to the mystery of its composition. It was clear that 3I Atlas was not simply a comet in the traditional sense. It was a hybrid part comet, part asteroid, and part relic of another world's formation process. The strange composition of 3I Atlas also raised questions about how many other such objects might exist. If our telescopes could detect only the brightest and largest of them, how many smaller, dimmer interstellar fragments were passing through our solar system unnoticed? And if each one carried a unique chemical signature, then the galaxy might be filled with an endless variety of materials, the raw ingredients for planets, moons, and perhaps even life. The idea that matter from distant star systems could travel across the galaxy and enter ours connected everything in a way that felt deeply profound. It meant that our solar system was not an isolated creation, but part of a greater cosmic cycle, one in which materials are shared, exchanged, and reborn in new forms across the eons. To scientists studying the data, 3I Atlas was like a cosmic archive, a record of alien chemistry preserved across the cold and silent gulf between the stars. Its strange spectral patterns, carbon-heavy composition, and mysterious behavior all pointed to a truth both humbling and exhilarating. The universe is endlessly inventive in its ways of building and preserving matter. Every star system writes its own version of the same story, one of dust, ice, and light, but each tells it in a slightly different language. 3I Atlas, in its brief, shimmering passage through our skies, allowed us to glimpse a few sentences of that vast and ongoing cosmic narrative from the moment it entered our solar system. 3I Atlas refused to play by the rules. It was as if this cosmic traveler had come not only from another star system, but also from another chapter of physics entirely. Every comet ever studied in our solar system, from the ancient Halley's Comet to the icy fragments observed by modern telescopes, follows a recognizable rhythm. They brighten as they approach the sun, they form tails as their ices vaporize, and they fade again as they retreat into the dark. But 3I Atlas defied this familiar pattern. Its behavior seemed inconsistent, unpredictable, and even contradictory at times, a puzzle that forced astronomers to question their understanding of what a comet really is and how it should behave under the laws of nature. When the first observations of 3I Atlas were made, astronomers expected a standard progression. As the object moved closer to the sun, the increasing heat should have triggered a steady rise in brightness. This brightening happens because sunlight warms the comet's icy surface, causing sublimation, the process in which ice turns directly into gas. The escaping gas drags dust particles with it, creating the iconic glowing halo known as the coma, and often forming a tail that streams away from the sun. Yet, in the case of 3I Atlas, this expected sequence of events never quite materialized in the usual way. Instead, its brightness spiked dramatically and then dimmed just as rapidly, as if it were breathing in irregular bursts rather than following a natural thermal progression. Such fluctuations left scientists puzzled. One possible explanation was that the comet's surface might be far more fragile and porous than those of typical comets in our solar system. Over billions of years traveling through interstellar space, the outer layers of 3I Atlas could have been weakened by radiation damage and micrometeorite impacts, leaving a brittle crust. As the sun's warmth began to penetrate this crust, pockets of trapped gas could have built up beneath the surface until the pressure became too great. When these pockets burst, they might have caused sudden jets of gas and dust to erupt, leading to unpredictable outbursts of brightness followed by periods of relative calm. This would explain why the comet seemed to flicker, not because it was fading away, but because it was venting in chaotic spurts, each eruption briefly illuminating it against the black canvas of space. But even that theory didn't account for everything. As 3I Atlas drew closer to the sun, it began to disintegrate much earlier than expected. Most comets can survive until they come within a certain distance of the sun, where the heat finally overwhelms their icy cores. 3I Atlas, however, fragmented long before reaching that critical point. This premature breakup suggested a composition or internal structure unlike anything seen before. Instead of a solid core, it might have been a loosely bound aggregate of ice, dust, and organic material, a kind of cosmic snowball barely held together by its own weak gravity. traveling through interstellar space for millions of years could have caused internal stresses and fractures. And by the time it entered our solar system, it might have been a fragile remnant of what it once was. Astronomers watched in fascination as the object's nucleus appeared to elongate, stretch, and eventually separate into multiple pieces. The Hubble Space Telescope captured faint images showing what looked like a trail of fragments drifting apart. Each fragment briefly flared as sunlight struck freshly exposed ice, then dimmed again as the material sublimated into space. It was a slow, graceful unraveling, the cosmic equivalent of a frozen relic turning to vapor before our eyes. This behavior reminded scientists of Comet Shoemaker Levy 9, which broke apart before colliding with Jupiter in 1994, but 3I Atlas was different. It was not torn apart by tidal forces or gravitational interactions. It seemed to fall apart under its own internal instability, as if the journey through the solar system had triggered a long-awaited collapse. What fascinated researchers most was the inconsistency in its activity. Normally, when a comet disintegrates, the resulting fragments and dust cloud follow predictable paths, fading steadily as the material disperses. But 3 Atlas showed signs of continued, irregular outgassing even after fragmentation, suggesting that pieces of it were still active, still venting gas as they tumbled through space. This indicated that the material inside was highly volatile, possibly containing ices that vaporize at much lower temperatures than water ice. Compounds like carbon monoxide or methane, which can sublimate even in the cold regions beyond Jupiter, might have played a major role in driving its erratic behavior. These volatiles are more commonly found in comets from the outermost reaches of the solar system, but in 3I Atlas's case, their abundance was unusually high, pointing to an origin in an environment even colder and more extreme, perhaps far beyond the frost lines of its home star system. Another remarkable anomaly was the shape and direction of its tail. In most comets, the tail forms a smooth, consistent line pointing away from the sun, driven by the solar wind, a steady stream of charged particles flowing outward from our star. But the tail of 3I Atlas seemed to twist and shimmer, shifting direction unpredictably, as though responding to invisible forces. Some astronomers propose that the object might have had a highly irregular rotation, causing its jets to fire in different directions as it spun. If it were tumbling chaotically, a motion common among small bodies, that could explain why its emissions appeared uneven and its brightness fluctuated so dramatically. Each rotation could have exposed new vents or sealed old ones, creating a constantly changing pattern of activity. For cometary scientists, such behavior was both confounding and thrilling. It meant that 3I Atlas was not just another interstellar object passing through. It was a natural laboratory for understanding the physics of materials that have existed far beyond the reach of our sun's influence. Studying its irregularities could reveal how comets from other star systems evolve over time, how their chemistry changes under prolonged exposure to cosmic radiation, and how their internal structures respond when suddenly reintroduced to stellar heat. It was a rare opportunity to witness the moment when deep space matter met sunlight again. After an unimaginable exile, the complexity of 3I Atlas's behavior also forced astronomers to revisit some long-held assumptions about what defines a comet. Traditionally, the distinction between comets and asteroids has been clear. Comets contain volatile ices that sublimate when heated, while asteroids are rocky and inert. But interstellar objects like 3I Atlas blur that line. Its unusual mixture of icy and rocky materials suggested that these categories might be more fluid than once thought. Perhaps many interstellar bodies begin as comets, only to lose their volatile layers over millions of years, transforming into asteroid-like remnants. Or perhaps they start as rocky fragments and later accumulate ice in the frigid depths of interstellar space. 3I Atlas could be a transitional object, one caught in the middle of that evolutionary process. Even its trajectory defied simple expectations. While the path of 3I Atlas through our solar system was clearly hyperbolic, indicating an interstellar origin, small deviations in its motion hinted at non-gravitational forces These tiny accelerations could be caused by jets of gas pushing it in unpredictable directions, the same kind of effect seen with Oumuamua, though less pronounced. Detecting such forces in an object so far from the Sun was astonishing, suggesting that the material on its surface was far more reactive than expected. This raised the intriguing possibility that interstellar comets might respond differently to solar heating than local ones, depending on their unique compositions and structural properties. In the laboratories of Earth, scientists attempted to model this behavior. Using computer simulations, they recreated a hypothetical comet with the properties of 3I Atlas, a fragile, porous body filled with volatile ices, spinning irregularly, and subjected to the fluctuating pressures of sunlight and solar wind. The simulations produced erratic bursts of activity, sudden fragmentation events, and unpredictable brightness changes, matching the real observations. This confirmed what astronomers had suspected. 3I Atlas was not a stable traveler. It was an object on the verge of self-destruction, a frozen relic unraveling under the touch of warmth for the first time in perhaps billions of years. What made its behavior even more fascinating was that it appeared to carry echoes of both its predecessors. Like 2I Borisov, it showed signs of traditional cometary activity, releasing gas and dust in measurable quantities. Yet, like Oumuamua, it exhibited unexplained variations in brightness and non-gravitational motion. It was as if 3 Atlas stood at a crossroads between two worlds, the known and the unknown, the familiar and the alien. It served as a bridge between our understanding of ordinary comets and the untamed mysteries of interstellar space. Through every observation, 3I Atlas reminded scientists that the universe does not conform neatly to human expectations. The physical rules we've learned from studying local objects may not always apply to those born under different suns. In other star systems, gravity, temperature, radiation, and chemistry interact in countless unique combinations, producing materials that behave in ways we have yet to fully comprehend. 3I Atlas, in breaking the rules of cometary behavior, demonstrated the creative chaos of cosmic evolution. The idea that even within the predictable framework of physics, the universe finds ways to surprise and challenge us. For the astronomers watching from observatories scattered across the Earth, each new image of 3I Atlas was like reading a page from a cosmic manual rewritten by nature itself. The patterns of light, the changes in brightness, the unexpected fragmentation, all of it painted a portrait of a comet unlike any seen before. It was fragile yet fierce, ancient yet alive with activity, familiar yet wholly alien. Its defiance of our expectations was not a flaw in our understanding, but a gift, a reminder that every rule in the cosmos is born from observation. And every exception pushes those rules a little further toward the truth of what lies beyond. When scientists first turned their spectroscopes toward 3I Atlas, they were expecting to find the same chemical fingerprints that define nearly every comet we've ever studied. For decades, cometary spectra have been like familiar songs in astronomy, dominated by signatures of water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and trace organic molecules. These compounds are what make comets the icy messengers of the solar system's earliest days, preserving in their frozen nuclei the primordial ingredients of planetary formation. But when astronomers analyzed the reflected light from 3I Atlas, what they discovered didn't fit the usual pattern. The chemical composition of this interstellar visitor was so unfamiliar, so unlike any cometary chemistry ever observed, that it challenged fundamental ideas about how comets form and what environments they come from at first glance. The light reflected from 3I Atlas seemed to carry the typical blue-green hue associated with diatomic carbon and cyanogen, two molecules commonly seen in cometary comas. But deeper spectral analysis revealed discrepancies in the intensity and ratios of these emissions. The carbon-bearing compounds were far more abundant than expected relative to water vapor. In our solar system, water ice is usually the dominant volatile, and its sublimation drives the formation of the coma and tail. Yet 3 Atlas appeared to be rich in exotic ices that don't play as central a role in local comets. It contained an unexpectedly high concentration of carbon monoxide and carbon dioxide, as well as hints of nitrogen-based compounds rarely observed in such quantities. This suggested that the comet had formed in an extremely cold region, far colder than the outermost reaches of our solar system, possibly in the distant peripheries of its home star's protoplanetary disk, where temperatures would have been so low that even nitrogen and carbon monoxide could freeze solid. To understand why this was so extraordinary, it helps to remember how comets form. In the early days of a star system's birth, clouds of gas and dust begin to coalesce around the newborn star. Close to the star, it's too warm for volatile compounds to freeze, so rocky planets like Earth and Venus take shape there. Farther out, beyond what scientists call the frost line, ices can condense, allowing gas giants and icy bodies to form. But for substances like nitrogen or carbon monoxide to solidify, the temperature must drop to nearly absolute zero, conditions that only exist at the extreme outer edges of a system or in interstellar space itself. The chemical fingerprint of 3I Atlas indicated that it was forged in such an environment, in a realm of deep, enduring cold, where molecules that would be gases even in the Kuiper belt could freeze into solid form. This discovery hinted that 3I Atlas might have preserved chemical information about an entirely different kind of planetary nursery, one colder, darker, and richer in volatile compounds than anything in our neighborhood. If our solar system's comets are snapshots of the conditions around our young sun, then 3I Atlas was a snapshot of another star's birth cloud, a chemical time capsule from a place humanity will never visit. Its unusual ratios of elements and molecules served as a cosmic fingerprint, revealing not only where it came from, but also how alien the chemistry of distant star systems can be. One of the most intriguing findings was the apparent scarcity of water relative to carbon-based compounds. On Earth, and in our solar system at large, water is the dominant ice, the substance most responsible for cometary activity. But 3 Atlas seemed to possess far less water than expected, and what little it had was locked beneath layers of other ices that vaporize more readily. This inversion, where carbon monoxide and carbon dioxide were more prominent drivers of activity than water, suggested that the comet had never experienced temperatures warm enough to alter its volatile inventory. It had likely been ejected from its home system before it ever approached its star closely enough for the water to melt or evaporate. In essence, it was a comet that had never thawed, an untouched relic. From the coldest corners of cosmic creation, the chemical anomalies didn't stop there. Infrared observations revealed spectral lines consistent with complex organic compounds, long-chain hydrocarbons, and possibly amino acid precursors. While organic molecules have been detected in many solar system comets, their relative proportions in 3I Atlas were astonishing. The presence of such compounds in an interstellar object supported the idea that organic chemistry, the foundation of life, is a universal process, not limited to our solar system. It implied that the same molecular seeds that may have helped spark life on Earth could be widespread throughout the galaxy, carried on icy bodies like 3I Atlas, drifting between the stars. For astrobiologists, this was an electrifying prospect. Every comet is a messenger from the dawn of its own world, but an interstellar comet like 3 Atlas is a messenger from another dawn entirely. The molecules it carried may have formed in molecular clouds billions of years before our sun was born. As they condensed into ices around a young, distant star, they became part of a frozen archive that traveled light years before entering our skies. When scientists studied its composition, they weren't just examining a comet, they were examining the chemical history of another star system, perhaps even another generation of cosmic evolution. The detection of certain isotopic ratios further deepened the mystery. The proportions of carbon-12 to carbon-13, nitrogen-14 to nitrogen-15, and oxygen-16 to oxygen-18 in 3I Atlas were subtly different from those found in solar system comets. These isotopic fingerprints act like cosmic barcodes, allowing researchers to distinguish the birthplace of an object. The variation suggested that 3I Atlas's parent star system might have formed in a molecular cloud exposed to stronger cosmic radiation or different stellar enrichment processes. Perhaps its home nebula had been bombarded by the remnants of supernova, injecting it with exotic isotopes that later froze into its comets. This means that by studying 3I Atlas, astronomers were indirectly learning about the life cycle of stars and how stellar explosions seed the next generation of planetary systems with diverse material. Another surprise was the detection of unusual refractory materials, minerals that form at extremely high temperatures. How could such minerals coexist with ultra-cold ices in the same body? This contradiction suggested that the material that became 3I Atlas had undergone significant mixing early in its formation. Grains that had once been near a hot star might have been thrown outward by stellar winds or gravitational turbulence, eventually freezing together with ices in the far reaches of the protoplanetary disk. This duality, the coexistence of fire-borne minerals and ice-borne molecules, painted a picture of a chaotic and dynamic system, where matter from vastly different environments mingled freely before being cast into interstellar space. This chemical complexity also hinted at the diversity of processes that shape comets beyond our solar system. Some scientists theorize that 3I Atlas might have been part of a young planetary system's debris disk, ejected after a close encounter with a giant planet. Others propose that it could have been expelled during the violent early stages of planetary migration, when massive worlds shifted orbits and destabilized smaller bodies. In such scenarios, objects like 3I Atlas would be flung into interstellar space, carrying with them the unaltered chemistry of their birth environments. Each ejected comet becomes a traveler drifting silently through the galaxy, occasionally captured by the gravitational pull of a new star, as 3I Atlas was. Briefly, Borisov interpret the unusual chemistry of 3I Atlas. Researchers used models developed for interstellar ice grains. In the vast cold of space, dust particles become coated with layers of frozen gases, forming mantles rich in carbon, nitrogen, and oxygen compounds. Cosmic rays and ultraviolet radiation then alter these ices, driving chemical reactions that create complex organic molecules. Over millions of years, these icy grains can clump together, forming larger bodies that preserve the chemical signatures of their environment. The surface chemistry of 3I Atlas matched this interstellar model more closely than any known solar system comet, suggesting that it had spent most of its existence exposed to the radiation fields between stars, rather than protected within a planetary system. Even the rate at which its gases sublimated revealed something extraordinary. In local comets, the release of gas follows predictable thermal models, governed by solar heating and surface composition, but in 3I Atlas, the outgassing rates didn't match these models. Instead, they showed spikes and lulls inconsistent with simple temperature-driven sublimation. This indicated that chemical reactions within the comet itself might have contributed to the bursts of activity, reactions involving exotic ices or trapped gases that had never been seen behaving this way in solar system comets. It was as if the internal chemistry of 3I Atlas was more reactive, more volatile, and less stable. Shaped by billions of years of exposure to cosmic radiation and interstellar chemistry, these findings collectively painted a portrait of an object that was both ancient and alien. The molecules within it were likely older than our solar system, forged in the cold darkness of a molecular cloud that once birthed another star. Each molecule told a story of stellar deaths that scattered heavy elements, of nebular clouds that condensed and froze, of violent ejections that cast fragments like 3I Atlas into the endless night. When that fragment finally entered our solar system, it carried with it the frozen memory of a world that no longer existed. Its chemistry wasn't just data, it was history written in molecules, a story billions of years in the making, now revealed in the faint spectra captured by telescopes orbiting our Earth. The revelations from 3I Atlas forced scientists to expand their definition of what a comet could be. It showed that comets are not simply icy leftovers from planetary formation, but complex chemical laboratories capable of preserving the fingerprints of entire star systems. The diversity of compounds in 3I Atlas demonstrated that the building blocks of planets and possibly life vary widely across the galaxy, shaped by different stellar histories and environmental conditions. In its chemistry, 3I Atlas carried not only the secrets of its own creation, but also a reflection of the cosmic processes that link every star, every planet, and every molecule in the vast network of the Milky Way. When astronomers first identified 3I Atlas as an interstellar visitor, they realized they were witnessing something profound. A physical messenger from another solar system, a traveler carrying the chemical, physical, and historical imprint of a place that no human eyes would ever see. It was not simply an object of curiosity, it was a fragment of cosmic history, a material link between distant star systems, and a living testimony to the processes that connect all of creation. Every photon reflected off its surface, and every molecule released into its coma told a story written not in words, but in the elemental language of the universe itself. 3I Atlas was not just another comet. It was a revelation about how planetary systems form, how they evolve, and how they send pieces of themselves into the dark to drift among the stars. To grasp the importance of what 3I Atlas told us about interstellar origins, we must first understand how rare it is to find such an object within our solar system. Most comets orbit our sun in long, elliptical paths, bound by gravity, returning periodically to the inner solar system before retreating into the outer cold. But an interstellar comet like 3I Atlas is fundamentally different. It travels on a hyperbolic trajectory, a one-way path that originates from beyond our sun's gravitational influence and will eventually leave our system forever. Its very orbit confirms that it was not born here. It came from another star's domain, flung into interstellar space long ago by the gravitational chaos of its native world. In that sense, it is not just a visitor. It is an emissary, carrying within its atoms the story of its home system's creation and evolution. Every planetary system, including our own, begins in a cloud of gas and dust, a nebula collapsing under the pull of gravity. Within this cloud, stars ignite, planets form, and countless smaller bodies take shape: asteroids, comets, and planetesimals. During this turbulent process, gravitational interactions between forming planets can send smaller objects hurtling into deep space. 3I Atlas was likely one of those exiles, a body ejected millions or even billions of years ago from its home system. For uncountable ages, it drifted through the interstellar medium, passing through regions of cosmic dust, magnetic fields, and radiation, until chance brought it close enough to our sun for us to see it. By studying 3I Atlas, astronomers were effectively studying a sample of another planetary system, without ever leaving our own. The composition and behavior of 3I Atlas offered clues about the conditions that existed in its birthplace. Its high concentrations of volatile ices like carbon monoxide and carbon dioxide, combined with its scarcity of water ice, suggested formation in a region much colder than the outermost reaches of our solar system. Such conditions would only exist in the deep periphery of a star's protoplanetary disk, far from the heat of its central star. This meant that 3I Atlas was a product of the frozen edge of another world, formed in temperatures near absolute zero, where even nitrogen and oxygen gases could solidify. This in turn revealed that other star systems, just like ours, produce a wide diversity of comets, each one reflecting the unique temperature, density, and radiation environment of its birthplace. The isotopic signatures of 3I Atlas deepened this insight. The ratios of different isotopes, for example, carbon-12 to carbon-13 or nitrogen-14 to nitrogen-15, serve as cosmic fingerprints. They vary subtly depending on the chemical processes, radiation exposure, and stellar evolution that occur in different regions of the galaxy. In 3I Atlas, those ratios did not match any known comet from our solar system, indicating that it came from a region of the Milky Way with a distinct stellar history. Perhaps its home star formed in a part of the galaxy enriched by ancient supernova, or in a denser, colder region of a molecular cloud where isotope fractionation occurred differently. These tiny variations in atomic composition carried enormous implications. They showed that our galaxy is chemically diverse, and that the materials forming planets and comets are influenced by their cosmic neighborhood in unique ways. As the story of 3I Atlas drifts beyond the reach of our telescopes, what it leaves behind is far greater than the trail of dust and gas that marked its brief journey through our solar system. It leaves behind a new understanding of who we are within the universe. Fragile observers suspended between curiosity and infinity, listeners to a cosmic symphony that plays on across the silence of space. The interstellar traveler came and went in a single blink of cosmic time, yet in that fleeting passage, it transformed our sense of scale, origin, and connection. It reminded us that the universe is not a distant spectacle to be watched from afar, but a living system that we belong to, one that breathes, evolves, and shares its essence across unimaginable distances. Through 3I Atlas, we learned that the galaxy is not static or isolated. It is a place of movement, migration, and exchange. The same materials that built this comet could once have built a world, and the same elements that make up our oceans and our blood may have been born around another sun. In that realization lies the most profound truth of all, that we are not separated from the stars, but made of them. Every interstellar object that visits our skies is a messenger from the wider universe, carrying whispers of creation, of chemistry, and of time itself. 3I Atlas was one such messenger, and through its discovery, humanity caught a fleeting glimpse of its own reflection in the vast mirror of the cosmos. It also reminded us that knowledge and wonder are not opposites. They are companions. Science does not strip the universe of its mystery. It deepens it. Every question answered opens 10 more. Every discovery invites new awe. 3. Atlas taught us that even the smallest fragment of ice and rock can reveal the infinite depth of the cosmos when we learn to see it not just as data, but as a story written in light and time. It showed us that the universe is not empty or cold, but filled with continuity, a ceaseless circulation of matter and meaning that binds every star, planet, and being together in one vast design. And so, as 3I Atlas fades back into the eternal dark, it leaves us with a quiet sense of belonging, a reminder that the cosmos is not something beyond us, but something within us. Its journey, begun in a distant system and concluded in the warmth of our sun, mirrors our own human journey, a search for understanding, connection, and place amid the immensity of existence. The comet has gone, but its message endures, that in every grain of dust, every shimmer of starlight, and every question we dare to ask, the universe continues to speak, waiting for us to listen.